Hello everyone, welcome to organolysis. So this is our concept problem solving part, and here in this video I am taking a question, the question which was came in CSIR-NET June 2015, as you can see here, and it came in for 4 marks. Okay, so the question was a major product formed in the reaction sequence, that is, you have given a substrate like this, and the reagent that is used for this reaction is SOCl2. Second, in the one step, that is SOCl2, this is a one step process. Okay, so in first step that you have given SOCl2 and the NaN3 and in presence of methanol, and the second step the reagent that is tertiary butoxide, and the third reagent is water, that is H3O plus. Okay, so let's start and how to solve this question. Let's see. Okay, so we all know the role of this SOCl2. It's generally used for this acid to chloride derivative, that is COOH2COCl, and there is a alternative reagents also used, that is PCl5. Okay, so in PCl5 or SOCl2 it can generally form COOH, that is COOH2Cl. Okay, so this is generally used by using SOCl2 or PCl5, both can does the same thing. Okay, now let's talk about this given substrate and the overall reaction mechanism. Okay, so now here I am written the substrate like this, C double bond O, COCl, here is a double bond O. Okay, so now see, SOCl2 is given to you and you get the product like this. Okay, so double bond, this is a Cl, and here you have the double bond. Okay, now the next step, that is in the first step that you have given NaN3. okay, and sodium azide. Now we all know this NaN3, we can break it like in this way, that is Na plus and N3 minus. So it's a nucleophilic type reagent, and it will generally attack to this ketone and this Cl, just because of not this ketone but this ketone only, just because of there is a leaving group over here and it can replace this Cl as well. Okay, so see what will be the product, this N3 minus, this N3 minus generally attacks over here, the bonds go over here and it will leave from the system. Okay, that you can get this product directly. Okay, so this is our C double bond O and this is our N3, and here you have the double bond. Okay, now let's see, we all know the structure of N3 also. Now we can write this structure in this way. Okay, let's see how to write the structure. This is a double bond. Now see, N3, the N3 have given, so we can write in this way, this N3, here is a positive and here you have the negative charge. Okay, now here is a double bond. Okay, see, this negative charge now there is an important rearrangement reaction, that is Curtius rearrangement. Okay, we all know what is Curtius rearrangement. If you don't know, I will make a separate video of what is Curtius rearrangement also, and there is a short part of this Curtius rearrangement is that Curtius rearrangement. Okay, this is our Curtius rearrangement. Now how this rearrangement takes place, that is, if there is a bond between this this overall, I will show you here in a short way, that is, if this bonds looks like in this way, that is N triple bond, and here is a plus and here you have the negative charge. Okay, now see, these bonds goes over here and these R with its bond pair electron, it migrate to this this nitrogen, and this N2 will leave from the system directly. Okay, so from here you can, from this carbon, this alkyl group is directly attached to this C double bond O, and after the migration of this Curtius rearrangement you get the product, that is R group is directly attached with this nitrogen center. Okay, so that is how we can get this product, and this intermediates are generally called the isocyanate intermediate. And how look like this one, that is in this way, N double bond C double bond O. Okay, so this is your isocyanate intermediate. Okay, and after the hydrolysis or anything else, the product takes place differently. Okay, so for this there is the same mechanism is follow for this reaction also. So there is a possibility of this Curtius rearrangement, and for this, and what will type of product that we get with these bonds go over here. This overall bond will migrate to the center, and this will leave from the system. Similarly, we get the product here is this, have the C, you have the nitrogen, double bond C, double bond O, methyl, here you have the double bond. Okay, so the first step is completed. Okay, so that is up to the first step. Now the second step, that you have the given the reagent, that is tertiary botoxide. Okay, so it's a non-nucleophilic base, so it is a base, and it's a non-nucleophilic in nature, so it cannot adapt to this carbonyl or this center. So not that, so it will takes a proton from here just because it is acidic in nature. So it will generally takes a proton, TVO minus, it generally takes a proton from here. So here you have the hydrogen, and these bonds takes a proton, go over here, and here the formation of this enolate intermediate. Okay, now see this one, this N, double bond C, double bond O, here you have this O minus, double bond. Okay, so this is our enolate system, enolate ion. Okay, so this is our enolate ion. Now the next step, and that is the important thing, is that now this isocyanate, this is our intermediate, so it generally not stay in this way. So the next important, and the importance of this question is that the bond ring formation. Okay, and how the ring formation proceed, that is these bonds, this negative charge go over here, and these bonds generally attach to this carbonyl center, and these bonds go over here, and it will breaks over this nitrogen center. Okay, so just because of the nitrogen is more electronegative. Okay, so your bond breaks to the nitrogen center, and after that you get the product like this. Okay, see the structure, to draw the structure is very much important. How do you draw the structure? Okay, so this is, now the bond formation takes place from this carbon to this one. Okay, so the bond is generally takes place, now there is you have the nitrogen, here the C, double bond O. Now this bond takes place from here, and here you have the double bond O, and this takes a proton from here, and it will get this secondary amine. Okay, now the important step and the last step is that is you have given this H2O plus, that is acid or H2O plus or water, we can say. Okay, now see how the next step and how the last part of this reaction is takes place. Okay, so see this OH minus. Okay, so water has H plus and OH minus, so this OH minus is directly attached to this carbonyl center, and there is a bond breaking takes place. And how this bond breaking takes place, let's see. This double bond, this OH minus directly attached to this carbonyl carbon, this bonds up over here and goes down to here, and these bonds will break over here. And why this negative charge is stable, it is just because of this this negative charge is adjacent to this C double bond O, and that is how this negative charge is stable. So that is why this type of bond breaking takes place by using this OH minus. Okay, now see the importance of this reaction is the stereochemistry, that in the given 4 option you have to predict the stereochemistry as well, and the perfect product as well. Okay, so keep in your mind that the stereochemistry of this reaction is very much important. Now see there is a double bond, okay, like this, C double bond OH, CO2H, that is one, and here you have the NH. Okay, so here you have the double bond, and here you have the negative charge. Okay, and one more methyl group is over here. Okay, now see CO2H, this CO2H generally goes back to the back side, it goes to the back side, and the methyl group goes to the above side. And why this type of this OH group is CO2 is in backside and methyl is in upside? It's just because of this. You have to predict from here the stereochemistry. Okay, so when we use the H3O plus, then it generally takes a proton from here, and you get the product. Now from here we get this one. Okay, and you have the NH, the double bond. Okay, so now this is in upside, and here you have the hydrogen, which is in also in upside. Then this methyl and hydrogen, the junction of this position is in upside. Okay, and the last thing of this methyl group is in upside, and the CO2 group, OH group is in upside. Just because of the attacking of this OH minus is very much important. Okay, so this bonds, this OH minus attack over the here, and you will get the COOH, which is in backside, and this methyl group which is in upside. That is why you get this product like this. Okay, so this methyl group is in upside and CO2H is in backside. Now you get the product. It is our final product, but you can, as you can see over here, the options that you have given in the both C and D, these junctions are in backside, and these two positions of this methyl and COOH also in different. Okay, so just because of this ring, this 5-membered lactam part is in your right side, but our product is this lactam is in your left side. So how to convert this one to the answer, the given answer script? You have to rotate this one. Okay, so you have to rotate, just you have to flip this one. Okay, so this lactam part is in your left side, and you have to flip this one like this. Okay, so that is how we can get this lactam part in your right side. Okay, so when we doing the same thing, that is your NH double bond O. Okay, so now see, we are just rotating this one, just flipped over this one. That is our rotation part. When we rotate this one, generally these junctions are in your with junction which is our in upside, which generally goes to the back side, just because like see the pen. Okay, so this is in your upside, this pen, but this part is this part, that is this black portion of this pen is in upside. When it just rotate over here, when this is in upside. Okay, so when it just flip to over like this black part is in your downside. Okay, so as you can see that this methyl group is in your upside like this, and when it just flipped over here like this, and this junction part is in your backside. Okay, so all the stereochemistry of this product will be changed directly. So junction is simultaneously changed from above side to backside, and the position of this methyl and COOH is also changed. That is, the methyl group which is in upside, it generally converts to this in backside, and the CO2 which is in downside, and it will generally comes up to the upside. And the final product that we get is the COOH is the above side, and this methyl group is in backside. Okay, now after the rotation we get our ultimate product. Now you can see that this 4-membered lactam that you have given, which is comparatively not more stable, so that is you can easily eliminate of this option. So option A and C you can easily eliminate, but you have to predict the option C and D between them. Now see, this COOH is in upside and this methyl group is in backside. Okay, so this is our final product. Okay, so this is our correct product. So from here we can see that this methyl is in, after the rotation, before the rotation, this methyl or COOH group is in, methyl is in up and COOH is in down. That is this one, but this you have to look the overall product and overall stereochemistry and what are the position of this lactam or this 5-membered ring. Okay, why I am saying it's lactam, it is just a amine group over here. If the oxygen is inserted over this NH group, it will be called the lactone. When O oxygen is replaced by this NH, and we generally called it lactam. Okay, so this is our lactam. Okay, so the option C is our correct answer. Okay, so I hope this video is very much helpful and very much informative for you, and If you find this video useful, and like this video and share it with your friends. And that's it for this video. Thank you so much for watching.